So good day class. Today we're going to be talking about Masonry. Masonry is a method used to determine the overall transfer function of a system represented by a signal flow graph. So this is an example of a signal flow graph that we're going to be tackling today. This is the formula given for Mason's gain. So it's the gain of each forward path times the delta of that forward path over the overall delta of the graph. This is it in its mathematical format. So the overall delta of the system is given as 1 minus the sum of individual loop gains plus the sum of two non-touching loops plus minus the sum of gains of three non-touching loops. Next, we have the determinant of the graph when considering only loops that do not touch the forward path. We're going to see this in our solving. And lastly, forward path gain is the product of gains along the forward path. So this is the example we're going to be tackling today. So first, we're going to identify our forward path because in Masonry, you need to know the forward path gains. Forward path is basically the path you can use to get from the input, that's RS, to the output, that is CS. So let's try to go in that direction. So we can go this way. We have passed G1, so we have to pass G1. Next, we can keep going straight. We keep going straight. This arrow is going this direction. So next, we have passed G2. And lastly, we're going to pass G3 here. And now we have reached the end. So we can safely say that our first forward path gain is G1, G2 times G3. Now let's see if there's any other path we can use. Starting from here and stopping here. So we're going to pass G1. Next, we can branch here because the arrow is in this direction. So we can branch up here, come here, and then go in this direction. Once we pass G1, we pass this one here, and we pass G3. So we can safe to say that our second forward path gain is G1 times 1 times G3, which can is the same thing as G1, G3, because anything times 1 is itself. Now next, we need to identify our loop gains. So loop gains is the product of branch gains found by transversing a path that starts at a node and ends at the same node. So let me show you that now. Coming back to our signal flow graph over here, let me take off all of this so that we can concentrate on our loop gain now. Okay, so now let's look for our loop gains. The keyword in the definition I just said is starts at a node and ends at that same node in a loop. So let's look at that. Let me show you what I mean. I can start from here and I'm going. This direction is going this way, so I'll keep going this way. This direction is also this way, so I can still keep going here. Now you can notice that I can actually come down here if I want to, because this arrow is in this direction. And I'm back to the same node I started from. So that this is one loop gain. Remember in the definition I said loop gain is the product of branch gains. So the product is G1 times G2, also pass G2 as well, times this minus H1. So we're going to write that out under our loop gains. G1, G2, and minus H1. We can also just write this as minus G1, G2, H1. Now let's check if we have any other loop gains. Coming back to our graph over here, let's check again. I believe we can move from this node. We can go in this direction. Then we can come down. Sorry, can come down in this direction. This is facing the left side, so we can take it as a loop and come back to this same node we started from. So this is another loop gain. We can write it out as G2 minus H2, which is same thing as minus G2 H2. So let's write that under here. So let's write minus G2 H2. This is the second loop we found. This is the first. Okay, next. Let's check if we have another loop gain. If we start from this node over here, we can move in this direction because the arrow is demarcating this area, and then move along this loop. You can see the arrow is in this direction. We've come back to the very same node we started from, so this is another loop gain. So let's write it under our loop gain table. This will be G3 minus H3. You can write the minus in front. This was our third loop. Now, looking back at the signal flow graph, I don't think we have any other loops we can go, because if we try using this path, you find that we don't come back to the same node we started from, so we cannot use this path. So that is all for loop gains. Now, next, let's just find non-touching loops, two at a time. Coming back to the signal flow graph, let me show you what that means. So we want to find two loops that are not touching each other. That's just what it means. Let me clean this up so that we can see what I'm about to draw clearly. Okay, so now we need to find two loops that are not touching each other. We already know the three loops we found during our loop gain. Let's check if any of them are touching each other. This was the first one, G1, G2 times minus H1. The second was G2 times minus H2. We can see that these two loops intersect with each other at this point. So therefore they are touching each other. So this is not the correct answer. Now let's check two other loops again. Let's go G1, G2, and go down times minus H1. Now let's check this G3 coming down times minus H3. We can see that these two loops do not intersect. Therefore, we have found two loops that do not touch each other. So, and that is G1 minus H1 and G3 minus H3. Let's write that out. Or rather, minus G1 H minus G1, that's this path, then G2, then times minus H1. So it's going to be G1, G2 times minus H1. I put the minus in front. So let's write this out under our non-touching loops two at a time. So that's going to be minus G1, G2, H1 times G3, H3 has a minus in front. Minus times minus is going to cancel out. So just give us G1, G2, G3, H1, H3. These are first two non-touching loops. Now let's get back to the graph and see if we can find another two non-touching loops. So let me erase this so you can see clearly. So you can see that if you start from here, this is one loop. And we also go for the G3. You can see that these two loops are not touching. Therefore, we have found another two non-touching loops, and that is G2 times minus H2 and G3 times minus H3. So that will be minus G2 H2 times minus G3 H3. The minus will cancel out. So we're going to just be left with G2 H2 G3 H3. Let's write that out. That will be G2 H2 G3 H3. Now, coming back to our signal flow graph, I don't think there are any more small structure that we're going to be able to find. So I think this is all. I believe this is all. Now, the third thing we're supposed to find is three non-touching loops. So let's see if we can find that. Let's start from here. This is one loop. This is another loop, but they are touching, and this is a third loop. You can see that we're not going to be able to find, we can only find two non-touching loops, but we are not able to find three non-touching loops. Therefore, there is no three non-touching loops for this particular example. So we're not going to have anything here. Let's just be zero. Now next we need to find the determinant of our graph when considering only loops that do not touch the forward path. How many forward paths did we get? We got two forward paths. This is one and this is the second forward path. So we need to find loop gains that do not touch the forward path. Now keep in mind our forward path is G1, G2, G3 and G1, G3. So where are our loops? Our first loop is G1, G2 times minus H1. You can see that it touches the forward path of G1, G2, G3. It touches the forward path. So therefore, this loop cannot be correct. Now let's try the second loop. G2 times minus H2. You can see this clearly touches the forward path of G1, G2, G3. So therefore, this is not correct. Next, let's try the last loop gain we have. You can see that it still touches our forward path of G1, G2, G3. So therefore, for our first, because K is values from 1, 2, 3, depending on how many forward paths you have. And we just checked the forward path. We found that there's no loop gain. So therefore 1. Now for our second forward path, that is G1, G3. We're going to check if any of our loops touch it. So let's look at G1, G3. I will add the 1 so that we can clearly see how the loops are touching. So now our first loop, G1, G2, H3. You can clearly see that it is touching the forward path. Next, let's try our second loop, G2 times minus H2. You can see that it's touching the same node as the 1. So therefore, it is not correct. Next, let's check our last loop. You can see that it touches the forward path. So therefore, for the second forward path, we do not have a delta k. So I'm going to go down here and equate it to 1. Now we have all the parameters we need for the Mason's gain formula. So here it is. We have found the gain of each forward path. We have found the delta of that forward path, and we have found this. So now first, let's compute our delta. So delta is equals to 1 minus sum of individual loop gains. What were our individual loop gains? We can find them here. That is minus G1, G2, H1, minus G2, H2, and minus G3, H3. Let's write that out here. G2, H1, minus G2, H1, minus G3, H3. Now next, plus our sum of two non-touching loops. Let's look at that. What we got? We got this. We got G1, G2, H1, G3, H3, and G2, H2, G3, H3. Let's write that out here. G1, G2, H1, G3, H3 plus G2, H2, G3, H3. Now minus our sum of three non-touching loops. But recall, we're not able to find that, so nothing is going to be there. Now next, we can simplify this. If we bring out minus from all these equations, we're going to find 1 minus times the minus outside here, leaving everything positive. Next plus our sum of two non-touching loops. Okay. So now We can write a complete equation. T of s is equals to what is the gain of each forward path? The gain of each forward path, this is it, forward path gain, 1 and 2. So we get our G1, G2, G3, and G1, G3, we'll write the one for the measure. So let's come back and write it out. G1, G2, G3 plus G1, G3, and 1. Now times, what's the delta of the forward path? You can see the delta of the first one is 1, and the delta of the second one is 1 as well. So we just write times 1. Or rather, we can just not write anything there, because anything times 1 is 6. All over delta, which is 1 plus G1, G2, H1 plus G2, H2 plus G3, H3 plus the sum of non-touchables, G1, G2, sum of two non-touchables, H3 plus G2, H3, G3, H3. And this is the final transfer function for our overall system. It's as easy as that. I hope you understood. Don't hesitate to leave your questions in the comment section if there's anything you do not understand. Okay, thank you for listening and bye.